Hello, everyone. My name is Lorraine Maji. I'm standing in for Farai. Welcome to the weekly OneQuantum Africa meeting. I would like to briefly talk about OneQuantum before I talk about today's speaker. So OneQuantum's mission is to equip our members and the wider community with strong local networks and access to the global community by offering events, summits, online communities, digital assets to them, as well as mentoring, careers, and financial support. Our vision is a supportive and authentic community platform for anyone active or interested in quantum tech, no matter their background, skills, origin, gender, or race. Sorry? Hello? I think we just lost Matthew. Can you guys hear me?
Yeah, we can hear you.
Okay. So that's fine. Oh, okay. Thank you. For Ms. Lazy, yes. So
you can still hear
I'll
me.
hand you over.
Is it Lorraine?
Yeah, we can. Yeah, we can still hear you. So thank you guys for Ms. Lazy, and I'll hand you over to her and she'll take this forward. Thank you so much for Ms. Lazy. You can take over, please.
Cool. Evening, good afternoon, everyone from where you're joining us from. Thanks, Lorraine, for opening up the session. And I believe today our chapter president from OneQuantum Africa Farai asked us as chapter presidents in the continent, I specifically for SA, to host this event because this is has much more truer closer more home to SA, since one of the first diamond mines was discovered here, the big hole that sits in the Northern Cape. So today we're joined by Matthew from Element 6, who will tell us more about how is diamond, far from we knowing it as being a jewelry that is set on crowns of queens, expensive rings. We never ever thought of diamond having those special properties that could actually be used for technological innovations, uses in medicine and imaging. So Matthew will tell us more about that. So I'll hand it over to you, Matthew. Go.
Cool, thank you very much. And thanks very much for giving. So before I get into the sort of main talk, please feel free to ask questions throughout, and we can deal with them as we come along. Although I can answer it. Just to give you a little bit of background about me and who I work for. So I work for a company called Element 6. So they're part of De Beers, or industrial African heritage. So specifically, the sort of background of De Beers, if you like, was back in diamond, which was mined diamond, and they didn't know what to do with it. They wanted to find industrial uses for it. South Africa. So we actually went to Zimbabwe, as one of the locations he went to, and Zaire as well, to look for companies that could make use of diamond. And from that sort of seed back in 1936, he then, De Beers Industrial Diamond was formed in 1946, so a little bit later, to find uses as a separate company out of De Beers to find uses for industrial diamond. And then going on from there, we then obviously, industrial diamond, then obviously started making diamond further down the line, which I'll get back into. My story comes into element 6. I joined in 2007, and I've been very fortunate to work on what I manage is relating to diamond quantum technologies. And that's what I'm going to talk to you about today. So let me share my screen. It's just coming through. There we go. So as I said, I'm Matthew Markham, and today what I'm going to be talking about is diamond quantum technologies. What I'm roughly going to do today is talk through how we make the diamonds. I'll talk a little bit about the different technologies and some of the little bit of history around that. I'll talk about the diamond applications. So what are the different types of applications beyond the quantum stuff? I'll just touch on those. But then I'll spend most of the other parts of the talk talking about diamond for quantum technology and the different, I'll give you a few different examples of applications. So I'll start with diamond synthesis, as I said. So why would you want to synthesize diamond? Obviously, it's a natural material. Well, it's all about engineering it so that you can make it the same every time. So these crystals here, these are all natural gemstones, all different shapes, all different sizes. And so you get quite a variety when you mine them. Obviously, the ones we mostly think of are the nice clear ones. But as I say, you get all these different types. You can get these spherical types of diamond. And what we want to produce is an industrialized material that you can make again and again with the same engineered properties. And that's all what I do, is focusing on generating consistent material. So how do you make diamond? So this is the carbon phase diagram. So obviously we're familiar with the two different forms of carbon. So graphite, the stuff you find in your pencils, or diamond, that sparkly gemstone. And the phase diagram basically plots the pressure against temperature. So what you can immediately see here, we live very much in this little corner down here. So room temperatures and pressures are down this part of the chart. And the immediate thing that jumps out is actually diamond is not actually stable. Graphite is a stable form of diamond, allotrope of carbon at room temperatures and pressures. Why doesn't it just therefore diamond immediately turn into graphite? That's just basically because you need to put energy into it to turn it from the diamond to graphite, a medium amount of energy. So if you heat diamond up, it would, it actually probably burn in oxygen, but heating it up, you could put enough energy into it, you could turn it into graphite. So let's start with how natural diamonds are formed. So natural diamonds are actually formed in this sort of zone up here. So sort of about 7 GPa, and I'll talk about what that is in terms of equivalent later, and sort of 1500 degrees. And natural diamonds were formed many, many billions of years ago, so roughly sort of 1 to 3.3 billion years ago. And they form in the sort of upper mantle. This is sort of the diamond stable regime. And so this is all where the diamonds are located. And how they get to the surface is through a particular type of volcanic event, a volcanic eruption, where the basically the lava bringing up the diamonds travels at a very fast pace up through this sort of 150 to 200 kilometers to get them to the surface. And that's important because, as I said, diamond wants to be graphite at room temperatures and pressures. So when you're moving this up through the Earth's surface, you want to make sure that you're not obviously putting enough energy in to turn those diamonds into graphite. So that's natural diamond synthesis. HPHT diamond synthesis, high pressure, high temperatures. That was the sort of, people were trying to emulate how diamonds were formed in the Earth. They knew that lots of pressure and temperature was likely used, and lots of experiments trying to achieve this sort of high pressure, high temperature conditions necessary to produce diamonds. And one of the first sort of claims was actually back in the 1890s, where a chap was basically putting graphite into a tube and heating that tube to high temperatures, therefore creating pressure within the tube and hoping to grow diamond. He claimed successfully that he grew diamond. The thoughts are that actually it was one of the tubes were exploding and he was risking his life, and therefore he wanted to get this scientist to stop doing that. Subsequently, after many years later, when we have lots of advanced equipment now to tell the difference between naturals and synthetic diamonds, they were indeed natural diamonds, they weren't synthetic. So the first actual technical success, our first diamonds that were synthesized were actually in Sweden by a company called ASEA. And so this is the group here, and they used a press which was designed by Balthasar von Platen, and he had this very unique press that he developed that allowed them to get to the high pressures and high temperatures, allowing you to form diamond. And they, as I say, they achieved that in 1953. However, they didn't really go and talk about it. It was the GE in America. These guys here, they were actually the first to publicly say that we've made diamond. And part of the reason I think these guys didn't talk about it is they thought they had more time. Their press that they were using was quite complex. It took months to build a capsule to go into the press, and so therefore the number of experiments they could do was relatively limited. So they just wanted to gather more data. They thought they got more time to do that. But actually, the guys at GE were successful and announced it in 1955. De Beers, so this is actually the De Beers team. They're looking actually at some X-ray data to show that they were growing diamond. They were first successful in 1958. So that's got a brief history of the high pressure, high temperature synthesis. Go on to the next page. Okay. So where is it on the phase diagram? So that occurs in this sort of regime, just above the this transition line here, just below where natural diamonds are formed. How do we do it? So we use, there's a couple of different presses that we use, but this is the basic method. You take your graphite, and you typically use diamond seeds as well. You put that into a chamber, a capsule. So this is roughly the size of a Coke can or something of that sort of size, a soda can. In that, you put some very important things, which is some metal solvents. And these metal solvents are the key bit in this process to make it happen quick enough so that you can do it on a depreciable time. So in the earth, you've got a long time for these diamonds to form. Obviously, we don't want to wait around for a long time, so we use these catalysts. Now, one of the key things that the guys at GE discovered, that you could use metal solvent catalysts, which basically carbon dissolves in and then precipitates out when you drive a temperature gradient across this capsule. This particular drawing here, the sketch, is called a belt press. So you have this, this is basically forms a belt. I'll show you a better image of it in a second. And then you have two pistons, one from coming to the top and the other coming from the bottom, creating the pressure. And as I said earlier, the pressures, so the 6-7 GPa gigapascal is the equivalent to say 5,000 cars or the Eiffel Tower topped on something like a jar of peanut butter or a Coke can. So it's very, very high pressures, but you also need to achieve high temperatures. So 1500 degrees, which is the melting point of steel. So these are really hard conditions that you've got to achieve. I've got to mention, to get the temperature in, we use something like a graphite heater, so a piece of graphite, something you can pass a current through, which you then use to get hot and heat up the capsule. So these are what the presses look like. They're quite large instruments. This is our press shop in South Africa. So this this is basically the press arm in here, and this image here is just one of the press arms here. And so this is the top anvil, and this is the bottom anvil, and they push obviously from the top and the bottom. And this thing basically is the thing that drives the force. And there's a bit underneath that also applies force up above. This image here, these are cubic presses, and I'll talk about those in a sec. But basically, they have applied pressure from all 6 orientations. So this is this little video here just shows you what the press looks like. So as I said, you've got this belt that holds around the capsule where you form a diamond, and with these 2 anvils coming from top and bottom. And this is a cubic press where you have all 6 orientations applying the pressure. So that's one way we grow diamonds. There is another way, which is using a chemical process called chemical vapor deposition. This is actually the process that I use to grow diamonds. Interestingly, you'll see it is not in the diamond stable regime. So it's in the graphite stable regime. So what we're doing is really using chemical processes to allow us to grow our diamonds. So what do we need for CVD diamond growth? There's a couple of very key ingredients. First of all, if you want to grow a diamond, you need a substrate of some sort. So if you want to grow single crystal diamonds, you need a piece of single crystal, or you can use other substrates, typically carbide forming materials as a substrate, which you can grow your diamond on. You need a source of carbon, and interestingly, it doesn't really matter what you use. You could use things like methane, and this gas-based chemistry thing. Basically, whatever you stick in converts over here by multiple reactions to this in the gas phase, and so it means you basically can use whatever processes you like. And in fact, people have done things like use tequila to make CVD diamond growth, although I'm guessing the purity is not that great because it's got lots of other things in it as well. So that's one bit. You need your source of carbon, but the real key magic ingredients in the chemical vapor deposition approach is hydrogen. So hydrogen does multiple different things. So first of all, it stops the sp2. So this is a type of bonding. So the bonding you get in graphite is called sp2. The type of bonding you get in diamonds is called sp3. And the atomic hydrogen etches away more of this more quickly than the diamond bonding. It also helps stabilize the surface, so it stops it turning back into graphite. It also creates the species, so it creates the methyl radicals, so carbon with 3 hydrogens, which are then basically the building blocks in the process, so they will stick onto the surface. And it also creates a site on the diamond so that we can put in the carbon. And this is the basic step where the surface chemistry, if you like, where you start with your carbon, a diamond surface, and then you reconstruct it and build new carbon into that. So you basically add in an additional carbon in here, forming your diamond. We can see that in this cartoon. So the white blobs here are our hydrogen atoms, and the grey ones are our carbon. So we take this methane here. We've then knocked off a hydrogen, forming a methyl radical, and then they come onto the surface and basically build the diamond up. You can kind of think of it like bricklaying. You're building one atom at a time. So this is one of the advantages of CVD, is that we can have much more control compared to the HPHT process in the ability to grow things like layers and add specific things into the diamond. So we can grow 2 different types of material using this process. So we can grow this polycrystalline material, and by changing the conditions, you can see very much this is of a black color, and you can make these clear ones which will polish up into windows. And by changing how you grow the diamond, you change things like the growth rate, but more importantly, you can change the properties. So you can change the grain size. So this has like a smaller grain size than this, which then scatters the light. But this is good for mechanical applications, and obviously this is good for optical applications. With single crystal, we start with a single crystal substrate and grow on top of that. We have our plasma, which is, I forgot to mention, is made by microwaves in the process. So we inject microwaves in the process to break up all the hydrogen and methane. And that's what then how we grow our single crystal diamond. And one of the advantages of a CVD as well is that you can see into the chamber. So this is a time-lapsed video of diamond growing, and by controlling the process you can add things into it as you go along, and say, for example, grow different layers of material. Okay, so that's sort of how we grow our diamonds. I'll briefly just mention how different types of diamond applications. So I won't and talk about why they are. So diamond is what we call an extreme material. So it has some really extreme properties. So when we think of diamond, we obviously think of the gemstone, but we also think of it being a very hard material. It's the hardest material or natural material that you can get. So it obviously has great mechanical properties, and that's used in a lot of applications. So think of polishing very hard materials, so things like the glass on mobile phones, or machining things like car parts, or machining again, mobile phones, electronic devices. They all use diamond to do that, and the reason they do that is the diamond lasts much longer than, say, a metal, and therefore you don't have to keep stopping to change your components in your machines that do the machining. The diamond has loads of other cool properties as well. Why does it have those properties? It's actually all due to the structure of the diamond. So everything I talk about in terms of the properties, and also all the quantum stuff, is related to the structure. So it's a very rigid structure with these very light atoms that are all strongly bonded, and they are all the same. So all atoms are equivalent, and all the bonds are equivalent, and that leads to all these interesting different material properties. We can engineer those properties, and by just tweaking things slightly. So there are a few different ways of doing that. There's introducing point defects, so that could be changing some of the carbons, swapping them out for other things. So this is the nitrogen vacancy defect. I want to hear a little bit about that later. We can change the isotopes. So normally there's 1.1% carbon-13, but we can change that. So this is particularly important for some of the quantum applications. It also has things like extended, what we call extended defect, things like dislocations, where basically the crystal lattice isn't aligned perfectly. There's this sort of kink in it, which creates something called a dislocation. Also, like in polycrystalline material, you've got multiple little crystals all linked together, and all with random orientation. So you get these things called grain boundaries. And you can also think about the surface, what the shape of the surface. All these things you can engineer and choose depending on the application. So diamond applications. So one is a thermal application. So diamond is the highest thermal conductivity of any material. So this is these are different grades of our diamonds. So this has been the highest thermal conductivity. And if you compare that to copper, it's basically 5 times higher thermal conductivity than copper. So this is used in things like thermal applications where you need to remove heat. So this is like a example where you've got a laser diode. So lots of laser light, which obviously generates a lot of electrical, you pass a lot of electrical power through it. A lot of that turns into heat. You need to remove that heat. And so things like diamond can do that. Diamond has the highest, widest window of transparency. So it's transparent from the UV into the far infrared and beyond. That means you can use it for things like laser applications as well. So this is like for a CO2 laser exit window. So diamond has the advantage compared to zinc selenide is that you can use it's transparent, those wavelengths, but it also, any light that is absorbed doesn't introduce heat. Basically, the heat is spread very quickly because of the thermal properties, meaning you can make better lasers. You can also use it to detect radiation, so things like neutrons and protons and alpha particles and things. You can make a radiation detectors, because diamond's what's called radiation hard. It doesn't break down as quickly as other materials, and that's again linked to the strong bonds. And they use this, for example, in the Large Hadron Collider as a detector to check if the beam's gone out of alignment. That's what one of those looks like. And you can even add things into it. So you can make diamond conductive by adding boron into it. And as diamond's very inert, it doesn't react. It's great for electrochemical applications. And this is here is just we're basically passing a potential, measuring a current, and these things here are basically reactions that are happening, and that's basically happening at the surface of these materials, so glassy carbon or thin film diamond. But if you have a bulk piece of diamond, which is what we produce, you don't get any of these parasitic reactions occurring, and so it's a very good system to do electrochemistry. And so this is an example here where we make actually a system called a Diapod, which we use for wastewater treatment. So it's good for basically breaking down chemicals in water and reducing them to something that's non-toxic. Okay, so that's enough about other applications. Let's talk about diamond for quantum technology. So why is diamond a great material for quantum technology? So it's basically, in most materials, you have things called spin, electronic spin. It's spin which is responsible for magnetism. And you can think of spin that's associated with electrons, think of like a little bar magnet. So it points north or south or north-south or south-north, depending on whether it's a spin up or spin down. And in most materials, you've got this spin, but it loses the phase. So it loses that orientation, which direction it's pointing in very quickly, because it interacts with phonons, which is basically heat in the materials, and also other nuclear spins. So if you've got like loads of other spins around, they interact with each other, and then you lose that spin information. And one of the sort of the key parameters is called T2, which is basically this spin lifetime. If I put this into, say, a north-south position, spin up position, how long is it going to stay there before eventually, when I measure it, it randomly have reorientated the other way around? And so that's called T2, and I'll mention that a few times throughout my talk. And that the lifetime of that is limited by this spin-spin interaction. So if there's all these other spins around, they interact with it, or a magnetic field external to the diamond, they will interact with it and cause this to spin to decay. So why, again, does it have these properties? So again, 100% linked to what I said earlier, this rigid lattice with this high symmetry means that you have these long spin lifetimes. And critically, and this is quite an important thing, you don't get much mixing of the spin and the phonons, which is this heat energy in the material. Normally, most materials, they will interact and you'll get this interaction and you'll lose that information. Therefore, the only way you can do anything with an electronic spin is by cooling it down to either liquid nitrogen or liquid helium temperatures. In diamond, that's very different. Diamond is a really good host because it doesn't interact. That heat that's in the diamond doesn't interact, such that the spin associated with defects in diamond can be effectively micro Kelvin, so like nearly 0 degrees, whilst the crystal itself is at room temperature. So let me introduce you to the defects. There's lots of defects in diamond that can be used for quantum. The NV defect, or nitrogen vacancy defect, is the key one, used for many applications. So it consists of a nitrogen, so replacing two adjacent carbon atoms, one with a nitrogen and one leaving it as a gap in the lattice. And this is actually an optical confocal image, a microscope image, and this is where we're seeing one single MV defect in otherwise very low, a high purity diamond. So what's really cool about the nitrogen vacancy defect, it has a large electronic dipole. That means you can easily see single defects. Basically, it shines very brightly. You can spin polarize it, and that basically means you can just shine light on it, and the spin will all align. So all of the spins in the diamond, all these nitrogen vacancy defects, the spin associated will all align when you just shine light on it. We can see that here. So if we take an electron in the ground state, so this is the sort of energy diagram. So this is increasing energy up here, and normally if you shine a photon or light onto a material, it will absorb, the electrons will absorb the energy and move into an excited state. And so if it starts in this state, the electron, then it goes up to this energy level, and then it will emit a photon, dropping a red photon, dropping back down. However, if it starts in this state here, and it absorbs a green photon, what it actually does is goes down via another route down into this bottom ground state. So that means you can do this sort of spin polarization. So by shining green light on it, whether it started here or here, it ends up in this state. So you all the electrons end up in the same spin state. Then you can apply microwaves, and then you can flip the spin state. So this is a spin up state, spin down state. You can flip the spins by using microwaves. And then you can read out by the same process. The amount of light that comes out depends on whether you started in this state or this state. So this state is we call a dark state, and this state here is the bright state. And so by measuring the amount of light that comes out after we've prepared our MV defect, we can read out how much or what is the final spin state of the MV defect. And as I mentioned already, you can do this spin manipulation and read out at room temperature, which is great for quantum applications. I will get back to some of the questions, I think, in the chat in a sec. So what that means is if we scan the microwave frequency, so I'm scanning the microwave frequency, what we actually observe if we measure the amount of light that's coming off is when we hit what we call a resonance, so we hit this energy level gap, we get it right, we actually get a drop in fluorescence. And that's what we're seeing here. As I increase my microwaves, suddenly hit the resonance and it drops down. And then as I go past resonance, the energy is too much and it's trying to pump up here. There's no energy level for it to go to, and it goes back to this sort of bright state. And so when we also then apply a magnetic field, you actually see these energy levels. So there's two energy levels here. They split due to an interaction with the magnetic field, and that we can work out what that magnetic field is by these are just fundamental constants. So they're physical constants that don't change. And this is the magnetic field, so we can actually work out what our magnetic field is. And this is one of the unique things about the nitrogen vacancy defect in diamonds. You can do all of these things. Next slide. So I'll go on to give you a little bit of background on how this all came about, because I think it's quite interesting, because it actually all started in South Africa. So the first demonstrations of that MV defect had these interesting spin properties was actually, there's a paper in 1977 in a very obscure journal called Diamond Research. It's very hard to get the access to that particular paper, and is by a couple of guys, Lobster and Van Wyk, Jan Van Wyk. And so I actually got this picture from my colleague. This is one of my colleague. He did his degree at the University of Witwatersrand in South Africa, and this is actually Jan Van Wyk here. So what he was doing, he was working, and we were actually funding this work. So this was actually funded by De Beers Industrial Diamond to investigate defects in diamond, because we're generally interested in these, what the properties of these defects were. And what he found, he was doing a particular measurement where kind of what I was showing you before, where he's applying microwaves on a diamond and also shining light on it. And what he found was that as he changed the lights that he applied, he found that he got a change in the signal that he was measuring. So basically, he was spin polarizing all the defects. And that's exactly what he described in his paper, that he was able to see this spin polarization of the magnetic levels. And he was also able to see this at room temperature. So this is a very, and even got hotter than that. So this was, you know, at the time, it probably was never really picked up much because it was, as I say, very obscure journal. No one really thought about it. The next real major milestone came in 1997 when a guy called Jörg Ratrup, who he was in France at the time then, but he's a professor at the University of Stuttgart. So his team basically demonstrated the first time room temperature magnetic resonance, which is the thing I was talking about on the previous slide, of single MV defects in diamond. And so similar to what I was showing on the on this image here, you're able to probe one single MV defect, and that's what he showed in this particular paper. And that's when the field really started to take off, because people started to think, well, actually, I've got this great spin in diamond that I can manipulate, and started to think about what you can do with it, thinking about quantum computing. Over the next sort of decade, up to sort of about 2005, all the guys that work, and there's probably about 5 of them around the world, were working on a diamond they called the Magic Russian diamond. There's more details in this, but basically they found one natural diamond that had some really nice defects. It had a very low sort of, it had NV defects, but it also had a very low population of other defects. So the spin lifetime was very long, and which was great. They cut the diamond up, and it went to several universities around the world, and they were then stuck in their university systems. Everyone was very protective of the Magic Russian diamond because it was by far the best diamond. But as I said at the start of the talk, all natural diamonds tend to be different, and they couldn't find another natural diamond with the same properties. Fortunately, this is where I started joining the story. Element 6 produced a material called electronic grade diamond, which had the same properties as the Magic Russian diamond, but now you can produce it on an industrial scale and repeat the process. And we sort of started using it in the field around sort of 2007. And this little map here just shows you the growth of diamond growth. Diamond quantum work over the past sort of, well, between 2007 and 2017, a massive rise in growth, and it's even gone beyond that. Obviously, hopefully, some of you guys listening, we can start to fill this bit in here as well. That'd be good if we can get some more work going on in Africa. Okay, so I've talked about how we make our diamonds. I've talked about the different, why diamond is interesting for quantum applications, but how do we therefore engineer it for quantum applications? So in an ideal world, what you want is your MV defects where you want them. So maybe near the surface of your diamond, maybe in a structure of some sort. You want the spins to be a long spin lifetime. You want all the defects to be the same. Ideally, you want the orientation of the defects, because they have 4 different orientations. You want all those to be the same. That's what you'd like to do. In reality, you get defects in a sort of more random position. It's much harder to control where they are. The surfaces are rougher. There's other spins in the system. There are other charges in the system. And you also get things like I talked about, dislocations, which also will affect the sort of properties of the material. So that's exactly what we've got to do as the sort of scientists that are growing the diamond. How can we bring some of these things under control? I'm not going to go into all of them, but I'll talk about some of those things, a few examples. So first of all, increasing the spin lifetime. Actually, this is a relatively easy one. So I talked about what spin is and this sort of spin lifetime, how long I can put it into a particular state, and the decoherence of the spin. And I said that's really dominated by all the other spins in the system. So other nuclear spin, for example. So carbon-13, for example, has a nuclear spin. Nitrogen has a nuclear spin. So all of these things can interact with your nitrogen vacancy defect and therefore reduce the lifetime of the spin. And you want that to be as long as possible, because that then allows you, if you're building a quantum computer, longer time to do measurement, or if you're building a magnetic sensor, it improves your sensitivity. Oh, so what affects spin? I've talked about those. So yeah, carbon-13, nitrogen, and other things that behave as little magnets effectively. And so what we did, and this is some work that we did many years ago. Firstly, that was sort of the back in 1954 when I talked about first forming diamond. The diamonds typically had carbon-13, which is the black spins here, and lots of nitrogen around. What we did in sort of 2002, this is when we did the electronic grade diamond. We removed all the nitrogens, very pure material, that increases the spin lifetime. And the next thing we do is reduce the number of carbon-13s, which improves it further. So that's moving from around 600 microseconds to a few milliseconds. So that's an example of how you can engineer the spin lifetime. There are many other factors. So this is a plot of that. So this is different amounts of carbon-13, and you can see with less carbon-13, the spin lifetime is increased. Other things are important. So I talked about dislocations. And dislocations basically induce strain in the material. That strain affects the properties. So we can actually engineer that away. So dislocations come from two features. This is our substrate, and this is our diamond growth on top. So if we've got dislocations in our substrate, they will propagate through into the bit that we grow on the top, or they can occur at the interface between our substrate and our new growth. So those are the two ways of how we can introduce dislocations. And so there's two ways then, or the way that we then remove them. One is careful selection of substrates. So remove substrate, pick substrate with low dislocations to start with, and you can see how we can make that. If we cut this vertically, we'd only have a few dislocations going, because they go in the growth direction, breaking the surface, and that would reduce them. And that's exactly what we've done in these pictures here. So these are X-ray images, with the dark bits are the dislocations. And so as you see, as we reduce the so we basically grow in a plate, cut it, produce this one, and then we're taking this one, cut it vertically to reduce this one. And by doing that process, you can reduce the number of dislocations. You can also, the also important thing is reducing these ones, and that's you can do by etching the diamond before you grow it. Nitrogen is important. So I talked earlier about reducing the nitrogen and more or less eliminate it completely. For some applications, you definitely want it in there. You want to add the nitrogen because you want lots of NV defects. You don't just want one, you want lots. And so some of the work we've been doing in the past few years is trying to optimize how much nitrogen we can get into the diamond whilst minimizing the other defects that form in the diamond. And so this picture here, the color basically indicates it's to some degree indication of the purity or the quality of the diamond. So brown diamonds, typically you've got other defects in there which you don't want. And by tweaking and changing the process conditions, we're able to grow diamonds with relatively high concentrations of nitrogen. So this is 18 parts per million, so 18 nitrogens per a million carbon atoms. And also you can see that the color is not brown. So we've managed to find conditions where we can grow diamond with very high nitrogen but low concentration of other defects. To create the NV defects in these high nitrogen materials, we radiate them with electrons, and that basically knocks out the carbon atoms, creating these gaps in the diamond lattice, and that's what you can see here by this is the concentration of these so-called vacancies as we increase the irradiation dose, and actually it changes the color of the diamond. So you by increasing the amount of vacancies, you get this sort of blue color, and you can see as we've increased the dose, we increase the amount of vacancies. We can then anneal the diamonds, and then we form these nitrogen vacancy defects. So this is just showing that we can do it time and time again. And this is what those diamonds look like. They look, so they're about starting with about 16 parts per million of nitrogen. We irradiate them and we create about 4 or 5 parts per million of NV defects. And then they give this a nice purple color. And what's really nice, this is the spin lifetime, and this is the nitrogen concentration, what you'd expect. This is actually another thing that Van Wyk did many years ago, and we are sitting on the line, which basically means we've made some very good high quality diamonds. I'll go into that, I'll skip over that. So we can tweak that and we can change the number. So that was, I talked about 16 parts per million nitrogen. This was, we can also make 300, that last slide was on 16 parts per million starting nitrogen. This is on 1 part per million. So you can tweak the conditions and change the concentration. So this is a material we now sell to the market. You can go further. So I talked about electronic grade diamonds, and these are confocal images showing single NV defects. So you can engineer it over all this range, and it feeds into the different quantum applications. And that's exactly what I'm going to talk about now. So I talked about how you do all these experiments, but what do you really need to build a quantum device? Actually, it's very, very simple. You just need a green laser. You can actually do this with a laser pointer. You're not going to make the best of devices, but you can use a laser pointer. You need a microwave source or RF source. You need a diamond, obviously. You need a magnetic field that just separates some of the energy levels, so you can just work with one set of energy levels. You need a filter, and then you need a detector. Same kind of stuff that, photo detector that's in your mobile phones. It's all very simple equipment. And this is actually an example where you can see the color changing, where we're just we have a diamond, we're shining our green light on it, and we're measuring the red light, and we're just changing the RF field, and you can see that it blinks. This is an example of a diamond magnetometer that we made with the University of Stuttgart. And so basically in this system, we have our laser, we have our diamond, we have our microwave, and we have our detector. And then what this system does is basically these different lines correspond to the different NV defects. So on the previous plot, I showed you just 2, but because there's 4 different orientations of the NV defect, you get 8 lines. And basically we were rotating this that little box, which is a shoebox size, around in a circle and measuring the magnetic field, the Earth magnetic field. And that's what this plot here is showing. This little compass is just showing the same thing. So great, you can do all this stuff. What's it useful for? So there's loads of different things that you can do, and I'll talk through some different examples. So magnetometry, so sensing magnetic fields, quantum computing, quantum communication, lots of different things. Let's talk through a few specific examples. So this is something we've done with Lockheed Martin. So the Earth actually has a different magnetic field depending on where you are on location to location. So this is a map of the Earth magnetic field. So if you can measure that magnetic field, the strength of it and the direction of it, then you can work out where you are on the Earth. And this is useful, for example, for global positioning. So GPS obviously relies on satellites, but those can be tricked or jammed. So having something where you've got a system that's on board that doesn't rely on external information is extremely useful. And this is something Lockheed Martin developed. So it's got a very relatively low, small size, weight and power, and can go on things like planes and things like that. You can also do things like measure materials. So there's quite a few groups now that are using this to look at interesting geological specimens. So in this approach, they have a thin layer of MV material, so maybe about a micron or so in thickness, and then they use that as imaging. So instead of having one detector, they have a CCD. So they have lots of different detectors, so they can measure across the diamond, and that allows them to map out the magnetic field. And so the first demonstration of this was in 2014, where Roger Fu here, he basically took a meteorite that he knew was around the formation of the solar system, and because they've got now this system where they can map out the magnetic field with sufficient resolution, they were able to work out then what the magnetic field was when the solar system was formed. So it's 54 microtesla. That was basically the magnetic field when the solar system was being formed. So starting to answer new and interesting things they just couldn't do because their other technologies just didn't have the resolution. You can also use this magnetic sensing for geology. So De Beers actually does this. I think this might be De Beers as Anglo helicopter. And so they have something called a squid, which is also a magnetometer, but it uses cryogenic. So you have to cool it down to liquid helium temperatures. And it's obviously very bulky, very challenging, expensive to run. But in principle, a diamond magnetometer you could make into a small enough to fit on a drone. And this is what a company who we're working with called OneQuantum are doing, building these small systems to map out magnetic fields. And the idea is that it will be able to tell you about the more information because it's got this vector or directional capability, can measure a range, measure the magnetic field and work out things like how much material of a particular thing is there. So this is my last example, which is on masers. So masers, exactly the same as a laser. The M in maser stands for microwaves. Microwave and is basically a microwave laser. So masers have been around for a long time. They were around before the lasers. And there's a few applications where people are using masers, so things like low noise amplifiers and frequency standards. But the limitations is basically because of the actual device itself. It doesn't operate at room temperature. It's or it requires cryogenics. It requires cryogenics or vacuum systems. So it's very, very bulky technology, very, very challenging to handle. So it's not really widespread. And so I've been working now with a few years with some guys at Imperial College in London. These guys actually did the first room temperature maser. This is their paper. So they made a maser out of pentacene, but this is an organic molecule or compound. And the challenge is it only could open in pulse operation because the base pentacene was getting hot and breaking down. So diamond, brilliant material for this because obviously it's got great thermal conductivity, so it doesn't have the same problems. And the way it works is you basically apply a larger magnetic field and you drive this energy level down below the ground state, and then you can create this so-called population inversion. So you can shine green light on it. The electrons go into this energy level, and then they drop down, emitting microwaves. And this is described in this particular paper here. So that was the last application. But what's interesting, I'd just like to link it back to what I was talking about earlier, Lobster and Van Wyk. The work that they did in their 1977 paper, they say that the spin polarization in this state at room temperature suggests that this phenomenon could be used to construct a maser. So they were very, very forward thinking in terms of what you could do and how it could work. But it took till 2018 to actually accomplish that. So that's all I've got to say. I've hopefully given you some insights into how we can grow diamond using two different techniques, high pressure, high temperature, and a chemical vapor deposition process. I've also hopefully given you some information on how diamond's unique properties make it suitable for quantum technologies with long decoherence times and the ability to easily read out quantum information, and also give you a flavor of all the different types of quantum technologies out there. And also, I like hopefully giving you some, showing you some of my stuff that's gone on in Africa, and really fed into this work. So I will stop sharing and go to the questions.
Cool, thanks, Matthew. Thank you for giving that awesome history of diamond to its current status in applications, in SA, and all over the world. So there are a couple of questions that our audience has. Got a bunch of them. So I'll start with Abdul. So in the first part of your introduction, you gave, for example, the developments. I saw that slide with a GIF file where you showed the quantum technological labs being developed all over around the world, but there's a limit in SA, in South Africa and towards the whole African continent. So he's just asking how much, if you can give a rough estimate, how much could developing a diamond-based quantum lab, how much will that cost?
That is a very, very good question. I'm probably not the best person to answer it, but I will give it my go because most of the stuff that we do in terms of like all the application sides, we do with partners and universities. I mean, in general, I mean, I can share a paper. I'll dig it out in a sec. It's actually very easy. You can build a setup to do a basic magnetic sensing type applications for maybe £1,000, $1,000 or something of that order. It's obviously not going to be a world-beating system because obviously you generally need better lasers in terms of stability and things like that. And I guess I'm guessing maybe 100,000 maybe would be more, a good system. But you can, like I say, you can play around with it with relatively easy technology. Like I'll paste a how to build a diamond system in the a link to a paper in the chat.
Yeah, if you could also like share your slides like later on with us, and we can.
I might be. I mean, obviously it'll be on the recording. I'd have to check whether I can share them for me.
Sure. Shall I go to the next question?
Yeah, go to the next question.
Yeah. So Dev Darts asked how much production of diamond in South Africa has been done, if you know.
So that's one of our main facilities. So we still have our facility down in South Africa that does HPHT. I mean, Element 6 itself, we have in just outside Springs is where our production facility is. We also have another HPHT facility in Ireland as well. But I think it's probably about 50-50 in terms of synthesis. And then that's the HPHT side. The CBD is done in the UK and in America.
Okay. Vishal is asking, could you just go back and summarize how an NV center system will actually demonstrate entanglement?
Demonstrating entanglement. Is that the question? Was it entanglement? Okay, so that's definitely a lot more complicated. So in that sort of system, you're having so entanglement, for those that are familiar with entanglement, is basically a particular special quantum property where two things are somewhat intimately linked, such that when you measure one of those things, the other one then immediately goes into a defined state, and you can't know beforehand what that state is. And so this is something that Einstein called spooky action at a distance. And I'm very fortunate to be working with some guys, a guy called Ronald Hansen based in the Netherlands, and they actually demonstrated for the first time that this spooky action at a distance actually was indeed a correct thing, because there's other theories or ideas, if you like, of how, I don't know, this guy, when before I do measurement, could tell this guy, oh, you need to be like this, you need to be like this, I'm going to be like this. And so they did some experiments back in 2014, 2015 to show that this these things are entangled. And the way they did that, where they had two different diamonds, and they basically, where they also had a third node, which they then shared this information to. So you basically do this weird sort of a swapping of quantum information, and you do that basically by measuring photons from the diamonds, and then you use basically a mirror or a beam splitter to sort of erase the information as to where that photon comes from, and that's kind of how you get this sort of entanglement process. Sorry, that's probably not a very good explanation, but
Cool. Tapiwa asked, what are the control electronics required to actually get feedback from the diamond?
Okay, so I mean, there are lots of different. What I talked about was a very simple, a CW process, or a continuous wave process, where you're just constantly shining light on. Typically, you do much more complicated pulsing schemes for that. So that you need things like arbitrary wave generators, a microwave source, so that's sort of the microwave side. You also probably need like you need pulsing for your lasers, so you need the name of them, but acoustic optic modulators to basically pulse the lasers as well. So they and then obviously that then gets all controlled by a computer.
Okay. I think this is the last question. I've just another for you. Robert Edwards is asking, how far is the technology from being commercialized in the quantum field?
So you can go buy a diamond device now. So there's, I didn't talk about it as one of the applications, but because you can make single NV defects and you can manipulate single NV defects, you can use it to make basically a nanomagnetic sensing system. So you can imagine having a little pillar with a single NV defect in the end, and then dragging that over a surface of interest where you want to measure the magnetic field, and that would allow you to image the magnetic field. So there's several companies out there, König and Q-Saber. They're both based in Switzerland that you can go and buy a device from and use it to sense magnetic fields. There are many other companies out there. So roughly, I reckon, 30 to 40 companies now developing diamond quantum technology, all at very different degrees of development. But those are the ones that are most developed. You can go and buy it today. Okay,
cool. And then now I'm just thinking of a rough idea here. If you had these multiple NV center defects, of course, you just have this vacancy in there. Wouldn't you create some type of like quantum memory for these? Maybe these vacant centers can be used as something that can store actual stuff. Is that something that could be tested and we can see like a commercial based use of?
Very much so. So typically, so like in any quantum device, like a quantum computer, you want to do something like called brokering, which is basically you know your system isn't going to be 100%. The memory is not going to be 100% perfect. So you want to be able to and retain that information. So what you do in those kind of circumstances for things like quantum computing is you take your NV defect and then you can get it to effectively talk to nuclear spins. Nuclear spins are much less affected by magnetic fields and stray magnetic fields and things like that, and they have much longer spin lifetime. So you can write that quantum information to your nuclear spin, and then you can then also read it back out via the NV defect. And so you can use those for longer term quantum memories. And there's several different schemes that people have developed to do those kind of things.
Okay. I think we don't have any much questions. So another one I just have within the field of like medical imaging around there, I've had like diamonds are like being used. What specifically, to what extent are they being used, or for what particular process?
Yeah, okay, so it's a very good question. So one of the projects that I'm working on a European project with a company called Envision based in Germany. And what they're developing is diamond systems where basically you take the diamonds, and diamond's got all these amazing great properties that you can easily control. But then you've got other things that you'd love to be able to control, but you can't do it as easy. So what they're trying to do is interface those two things. So take your quantum system, your diamond that you can control, then they want to transfer the spin information, so the fact that spin polarization, from that outside the diamond into another molecule. So the particular molecule we're looking at is a molecule called pyruvate. So pyruvate is a metabolite. It's something you find naturally in your body. And so what they want to do is take carbon-13 tagged pyruvate. So there's a carbon-13 associated with it. You spin polarize that carbon-13, and then you feed it to somebody. You then go in an MRI machine. Now, the fact that you've just taken something that has a carbon-13, which has all the spins polarized, means that it effectively lights up in the MRI machine. So in a typical, when you go for an MRI, you're applying a large magnet to your body, and probably one in about 10,000 of the hydrogen associated with water and other things in your body, they're the things that align. But with this sort of process, this hyperpolarization process, you're taking a lot more of those spins, and you've got therefore much more a larger readout. And because you're doing it with the molecule, you can then target particular things. So we're targeting for cardiovascular disease.
Cool. And then if one wants to actually work with diamond, study it, what will be the routes they should take? Perhaps if they want to be on the development side of things or the research side of things, what will be the natural route they should take?
Again, as an excellent question. I mean, so one of the things, and I think one of the reasons, and I'll go back to that growth video that I showed you earlier, one of the reasons I think a lot of people moved into this space is the barriers to get into it compared to some of the other high-tech quantum stuff are much lower, and that's because of the I mean, even that to us, 100,000 is a lot of cash to buy equipment, but in comparison to many other technologies where you've got to set up, refrigerated technologies, so you need liquid helium and all those other kind of things. It's a much cheaper way to start. So that's part of the answer to that question. And the other part to it is, okay, so you can buy the technology and it's relatively easy. How do I get into it? To be honest, I found this community, and one of the things that's very good about it is it's very collaborative. So to be honest, I would just start talking to people, find guys at other universities, and generally they're very happy to share information and get people started in this area. I know many of the guys that I've worked with have gone around to many other universities and just set up their first confocal system for them so they can get going.
Okay. Last one. Any research group or institution you're particularly working with that is developing like a quantum based application, or just looking towards that development of like a quantum based or and diamond based device or solution?
So I personally believe in open innovation and the development of technology that way, and I think that's, again, I think one of the advantages of this particular community is they recognize that the problems we're trying to solve are hard problems, and therefore we need to do it together rather than hiding away and going, I'm going to keep my bit and not talk to these guys. So they generally talk to each other. So I've been very fortunate that I work with many of the people around the world. I don't know how many in total that people I've worked with, but so the main groups that I've worked with are, I mean, there's lots of companies out there, but sort of academic groups, your graduate group at Stuttgart, for example, Federal Ulm. There's several more in Germany as well, in the US. There's Harvard, so there's quite a few groups at Harvard, Marco Lonka, Misha Lukin, as well as Ron Woolsworth, who's now at University of Maryland. In the Netherlands, Ronald Hansen and Tim Tamagno. Yeah, there's a long list.
Yeah, okay. What's the best way to stay in touch or connect with you? Where can we find you?
I think I didn't go to my acknowledgement slide. I'm just recognizing that now, that I have all those guys that I just mentioned on those slides, because without them, we wouldn't be able to, we wouldn't be where we are today with the technology. I am on LinkedIn, so just reach out to me on LinkedIn.
Okay. Well, I think now we can, if there are no more, I don't think there are any chats from the audience or any questions, I mean, from the audience. We have then our one-on-one networking, which we call it like a cocktail party, where there's a one-on-one matchmaking. Then there we could get to know each other then on a personal basis, get to ask you even more questions. So Lorraine has just put on the link there. If you would like to join us after this, please do. It's on the Run the World platform. Okay.
So you just connect and then
you just have to sign up. Yeah, correct. Okay. Great. Thanks, everyone. Thank you, Matthew, as well. We'll keep in touch with you, and I'm sure even the rest of the chapters, OneQuantum chapters we have here in the continent, will call you to say, give us an intro into diamond sensing, how can we use it, and just also I think we'll take an opportunity to say next week on the 26th, Quantum SA is hosting an event that is the first quantum community event for SA. So details will be shared. I think most of the people who are here, I have the email, so there's a newsletter that will be out just to get to know more what is happening within the country as well as the continent and the global world at large. Thanks, everyone. Yeah.
Okay, cool.
Yeah, see you at the cocktail party.
I'm going to try and join.
Yeah.
I will be there if I can. I'm trying to work out how to do it. Cool.
Okay.
Thanks, everyone.
Thanks.
Bye-bye.
Thanks, everyone.